So in 5.1, we see that in order to find area underneath the curves, we're going to begin with an approximation procedure. Then we're going to take, eventually we're going to take the limit of that approximation procedure, and that will give us what we're going to define as the area underneath the curve. But working with limits and those Riemann sums that you saw in the video is very clunky. Okay? So although calculus would still be just as beneficial if we always had to use those limits and always had to use those Riemann sums, the real benefit of calculus comes from the fact that we can use, or the real benefit of the second half of calculus comes from the fact that we can use the tools that we developed during the first half. Okay? So although we've got a week and a day left, for the second half of calculus, that's really all we need. Okay? But like I said, I want to go through the second half of the course, the second half of Unit 5 somewhat quickly, so you get so you can begin working on the mechanics, because that just takes practice. And then we'll go through the theory during the first half of next week. Okay? All right. So I want to define something that we didn't quite use in the video. We didn't use this term in the video, and that is the term net area. And I want you to contrast that with total area. Okay, so sometimes we'll be talking about net area, sometimes we'll be talking about total area, but we're going to begin all of our discussions with net area. Okay? So first of all, let's just give an interpretation of what we mean by net area. So suppose we have this function right here. And let's say we've got this function between a and b. Okay? And so we want to talk about, well, how do we find the net area between the curve and the x-axis? Okay? So I want you to think about that word net just a little bit. Okay? And again, so if we talk about the total revenue of a company versus its net profits, okay, revenue would always just be a positive quantity. It's just money coming in, versus net, which is a difference between two things. Now, that's how I want you to think of that word net here. So we're going to develop a tool that's going to compute this area underneath these curves, but we need to know how it works. Okay, so we'll go through the specifics of this tool next time, but we'll see that our tool is going to count regions that are above the x-axis as positive quantities, and regions that are below the x-axis as a negative quantity. Okay? Now, if we want total area, what do we have to do? We just have to make sure that we break it up between the regions where it's positive and negative, and we just change the sign on the negative regions. Okay? But our tool that we developed calculates net area. Okay? And this is how we're going to express the net area underneath the curve. We're actually going to define the net area underneath the curve in section 5.2, but for right now, let's just talk about how we're going to express it. Okay, so we're going to say that the net area is given by this symbol right here. I want you to first think of this as an entire symbol. I think that it's very important that you realize what type of object this is. This symbol stands for the what? It stands for the net area underneath the curve, right? So what type of object should it be? This is an important math skill, identifying the object you're working with. If you're looking for a net area, what would you expect as an answer? Give me an example of an area. Sure, so the units will be squared on it. Good. Not necessarily a ratio. Would you expect me to say it's the sine of x? That's the area underneath this curve is the sine of x?
It's the value.
It's a value. Specific. It's a finite value. It's a number. If it can be finite, yes. Good. It's a number. So it's important that you realize that this quantity right here is a number. Right? It might be the number 35. That is the area underneath the curve. It might be the number pi over 2. That's the area underneath the curve. But it's got to be a number. Okay, so this is the first thing you need to do, is recognize the difference between the indefinite integral that we introduced in the last chapter. Okay? I think it's always very important to separate when you learn indefinite integral with when you learn definite integral, so that you can kind of classify them as two different objects. What was the indefinite integral? It was an antiderivative, which was what? A family of functions. Okay. What type of object did you get when you took the indefinite integral? You got a family of functions. Or if you just want to say you got a function, good enough. Okay. When you took the indefinite integral, you got a function. When you take the definite integral, you get a what? A number. What does that number represent? The net area underneath the curve. Okay? So, we've already said this. This symbol looks very similar to what we wrote as our indefinite integral, but of course we're going to call this the definite integral. How do you distinguish between the two? Yeah, you got this x equals a number and x equals a number in both the numerator, or both the top and the bottom of our integral symbol. Okay? So we've got that x equals a to x equals b. That's how you recognize, oh, I'm talking about a net area here, not an antiderivative. Now we use the same symbol because in a minute we're going to see that the calculations are similar. Okay, but I need you to distinguish between this versus this, which is an indefinite integral which returns a function, more specifically a family of functions. But if you want to just say it returns a function versus this returns a number. This is absolutely critical going forward. Okay. I was going to say something else about this. We'll see. I'm sure I'll say it at some point. Okay, so what I'm going to do then is jump to the main result of this section, which is the fundamental theorem of calculus. Okay. How important is something called the fundamental theorem of calculus? It's fundamental, right? Okay. This is going to be something that connects the two different big ideas, finding the area underneath the curve with the tool of differentiation, or specifically the tool of anti-differentiation. We're going to see a connection between the two, and we're going to spend some time exploring that because it's important to learn that intuitive connection between those two types of ideas. But for right now, I'm going to jump. In fact, we're going to skip the first half of the first half of the fundamental theorem of calculus and just give the second half, which is the most practical on a day-to-day computational level. Okay? So this is what it says. Okay? Suppose f is continuous, then if I ask you to find the area underneath the curve from x equals a to x equals b of f of x dx, if you want to compute the definite integral, if you want to find the net area of a region, you're going to do so by simply calculating capital F of b minus capital F of a, where what does capital F represent? And this part's a little bit tricky, we'll talk about this. Capital F of x is any antiderivative of f of x. It turns out that continuity is more than we need. We can relax that a little bit, but we're not going to worry about that at all. That's for another. Okay, so let's put this into practice. Okay. Let's look at the graph of this function right here. It continues on downwards. Here's the graph of f of x is equal to minus x squared plus 4. And we want to find the area of this shaded region right here. Okay. Well, where does our shaded region start? It starts where? At what x value? At x equals 0, and we compute it until we get to x equals what? What's that intercept? What's that intercept? 2. Okay. All right. So I might just show you a curve. Okay, so the first thing you do is know how to translate that curve question into a calculus question. Okay, so everyone, let's write the definite integral from x equals from x equals where? 0. We customarily go left to right on this. X equals 0 to x equals 2 of negative x squared plus 4 dx. So what does that represent? I know it looks similar to our antiderivative symbol, but what does it represent? It represents the net area underneath the curve. It is the definite integral. Okay? Hopefully you're no longer calling it the S thingy, but I need you to take it one step further. Okay? We need to call this the definite integral versus the indefinite integral. Okay. So, well, that's a lovely thing to write, but how do we actually compute it? Well, in section 5.2, we will compute a couple of these the long way, and we will find out just how miserable that is. It's kind of similar to when we did the limit definition of the derivative. There is a limit definition to the definite integral, and we will do a couple of those by hand, but not many, because they are tedious, way more tedious than finding the limit definition of the derivative. Limit definition of the derivative. Okay? But we're skipping to the main result here, which is the fundamental theorem of calculus part 2, which says rather than worrying about the definition of this, we can go ahead and just give an antiderivative of this function evaluated at the two endpoints. Okay? Now, that task of expressing this thing right here, an antiderivative evaluated at the two endpoints, that's way too much generally for us to do in one step. So usually we do it in two steps. In the first step, we find an antiderivative, reminding ourselves to evaluate it at the two endpoints, and then in the second step, we do it. Okay? So what is an antiderivative of our integrand thing inside the integral? What's an antiderivative of that?
X to the third over 3 plus 4x plus c.
Close?
1/3 x to the third.
Well, yeah, he said over 3, but what's the sign on it?
Oh, negative.
Yeah, so we get negative 1/3 x cubed plus 4x. Now, I said I just need you to give any antiderivative. So here I'm not asking for the antiderivative, right? So I'm not going to put plus c here. Okay? In fact, I'm not going to write anything there. By not writing anything there, what am I choosing as the constant? I'm choosing 0. Okay, that's the best choice to make. All right? Now, careful. What type of object do I have on the left here? What type of object is this?
Definite integral.
The definite integral, which is a value, which is a number, right? What's over here? Does a number equal a function? No. So this is supposed to read evaluated at the two endpoints. So what I do is I just remind myself to evaluate it at those two endpoints. Okay? I don't have a name for that symbol. I just call it the evaluation bar. Okay? I don't know if there's a name for it. I can't remember. We just write it. Don't forget it. Otherwise, you've said that a number is equal to a function, which is not true. Okay? So how do we actually use this? What this is just a reminder step that's going to say now, take the upper limit of an integration, plug it into the function, plug it into an antiderivative, minus the lower limit of integration. How are we doing? Okay, so let's see here. Let's clean this up. Let's see. 2 to the third power is 8, so we get minus 8/3 plus 8 minus a bunch of zeros. Okay. So we get, let's see here, 8 minus 8/3, that'd be 24/3 minus 8/3. I think we get 16/3. Okay. What does that 16/3 represent? That area of the green shaded region, right? So if you had this parabola in your living room and you wanted to carpet it, how much carpet would you buy? You'd buy 16/3 square feet, or whatever your units are of it. Okay? That's the real world interpretation of this. Okay. Let's do it again. Okay. Let me just take this question over to another spot. This is for number 5, but I just... All right. So for number 5 here, let's find the area of this shaded region. Okay, it's going to look similar. It's still going to be the function f of x is equal to, it still goes down this way. It's still going to be the function f of x is equal to negative x squared plus 4, but the shaded region is now going to go, we're going to shade this part and this part, and we're going to go to where x is equal to 3. All right, this is a really important conceptual piece to this. The definite integral doesn't compute, so I sort of lying when I gave you that carpet analogy. I was sort of lying when I gave you that carpet analogy, because when we find the definite integral, we don't find the total area. What do we find? The net area. And how will the definite integral count each of these regions? It will count this region how? As positive, but it will count this region as negative. So how should my answer compare to my previous answer? It should be less. Does that make sense? That's an important conceptual thing to realize. That the way the definite integral works is that we'll count those as negative. For those of you that were comfortable with last night's video, you saw that, well, you didn't see this, but we could just extend. If I draw these rectangles below the curve, then when I take the height of the rectangle, which is negative, times the width, I get a negative number there. So that's why it outputs a negative, just by construction. Okay, so what am I asking you to find? I'm asking you to compute the definite integral. Fill out the rest of it. You fill out the rest. Check with your neighbor. See here, we're computing the definite integral from what are my oh, that's what I was going to say. We call these the limits of integration. That's what I'd forgotten earlier. What do we call these? Or sorry, I just told you. What are the limits of integration here?
0.
Yeah, from x equals 0 to x equals 3. Okay, in this problem. Our function hasn't changed, so it's still going to be minus x squared plus 4, what? Do you need the dx? Oh boy, you betcha. You saw this last time. Remember when you looked at 5.1, you saw all those delta x's? Okay. In the limiting procedure, we replaced the delta x's, which was the width of the rectangle, with differential x, which is the which still stands for the width of those rectangles. So do you still need that? Yes. Okay. But it also sort of it gets wrapped up into the woodwork when you do the antiderivative. All right, so let's actually compute this by the fundamental theorem of calculus part 2. Rather than using Riemann sums to compute this area, okay, rather than using those Riemann sums that you saw in the video, we're going to go ahead and just give an antiderivative of this. What do I have to write? That evaluation bar from x equals 0 to x equals 3. Do you need that? Yeah. I emphasized that in my other class, and then I'd go around and half the people wouldn't put it. Yes?
Can I just put 0 and 3 for A and B?
Yes.
Okay, cool.
Okay. All right. So let's see here. This is going to be minus 1/3 times 3 cubed plus 4 times 3. And then I'm getting the hang of things. There's no constants here. This is a polynomial, so just to save myself some time, I know that's going to be 0. You're welcome to do that. Do look ahead on that. Okay, careful, will it always be 0 if the lower limit of integration is 0? No. If there's an e to the x or cosine of x, no. Okay. Or if there's a constant term, okay. So, let's see here. I think we get 3 cubed is 27 times minus 1/3. I think we get minus 9 plus 12. So I think we get 3 as the area of this shaded region. That's nice. Rarely do you get nice numbers in this procedure. How come? Because often you use the power rule, and the power rule often introduces fractions. So oftentimes these don't work out nicely. That's just life. Okay. What else do I want to say? How does this number compare to our 16/3 from before? Well, 16/3 is a number a little bit bigger than 5. This is the number 3. So what happened? The definite integral counted this region right here as negative, so it took our 16/3 and wrote it this way. It took our 16/3 and then subtracted this amount from it. By the way, that opens up a really interesting idea here that we can do with our definite integrals. So let me show you this, this property. I hope you have room for it. Okay. Let me show you this property. If I take the integral from a to b of f of x dx, I could break it up as the integral from a to c of f of x dx plus the integral from c to b of f of x dx. In terms of what you saw in last night's video with the Riemann sums, one way you could imagine that is rather than adding up the area underneath the tire curve, you just go halfway or part way, you just go to C, and then you pick up where you left off, adding up the rest. And that's true, that's just a property of addition by its associativity. Okay? Does that make sense? How we doing? MC? Okay, so where did I lose you on the property or did I lose you on something before? Okay, on the property. So let's look at this problem here. How could we have done this problem? Okay. If I asked you for the definite integral from 0 to 3 of minus x squared plus 4 dx, what I'm saying is you could have gone from 0 to 2 of minus x squared plus 4 dx plus the integral from 2 to 3 of minus x squared plus 4 dx. Do you see what I did there? So I broke it up into two different pieces, adding up first from 0 to 2 and then continuing on from 2 to 3. Does that clarify?
So with the first, not function.
Definite integral?
Yes.
Evaluate to? Same
of
six.
The property, would it be a to c instead of a to b?
Well, so this is what we started with. If it originally goes from a to b, you could stop off at c and then resume.
Okay, so we're saying c is between.
Great question. It actually does not have to be in between.
Okay.
It doesn't have to be in between, which is why we use c. Okay? So one way of looking at this, okay, is we will learn later that the definite integral of a position function calculates your net displacement. We know what a position function is, right? Excuse me, that's a lie. The definite integral of a velocity function calculates your net displacement. I said position, I should have said velocity. Okay? So we've already seen that, right? The antiderivative of velocity is position. Well, the definite integral of a velocity function gives you your net displacement. So, rather than calculating, okay, what was my displacement as I went from here to here, another way you could do it is say, what's my displacement as I go from here to here, and then from here to here. So that C wasn't in between the two, but the difference still would give us, my net displacement. So it still works out. Yeah, great question. Okay, so this was 16/3, and then in fact we could actually figure out what this would be, because we got 3, so it would have to be 9. So what would that have to be? Help me out, folks. This would be negative 5/3, right? Because when you add them together, what do you get?
9/3.
You get the 9/3 or the 3 that you were supposed to. Okay? So what I'm saying is, rather than finding the total net area, we already found out that was 16/3. That's a 16. We already found out that was 16/3. We could then compute this, find out that it was a minus 5/3, minus 5/3.
Wait.
No,
7.
7/3. Thank you. Kick me out of math class. Minus 7/3, which would give us the 9/3 or the 3 that we were supposed to get. Okay? Questions on that? We're going to get more practice with this as we go along. Okay. I want to do this one more time Okay, so let's do it one more time. Let's find this area. This is again the function f of x is equal to minus x squared plus 4. And we're going to find this area. So what's that between? That's between x equals -2 and x equals 2. Okay? I'd like you to do all the work. Okay? Don't shortcut anything. I mean, you can shortcut, you don't have to prove 1 plus 1 is 2, but don't use the work from previous problems. Okay? Go ahead and compute that. So let's look at the setup here. This is the definite integral from -2 to 2 of minus x squared plus 4 dx. I didn't write x equals -2 to x equals 2. You don't have to write that. You do have to put the numbers there. Okay? But there will be times where I will rewrite the x equals because I want to emphasize that these are in terms of the variable x, because we're going to do changing of variables here soon. Okay, so it's kind of cumbersome to write x equals every time, but sometimes in fact, I would encourage you until you feel really, really comfortable with this, keep writing the x equals. Okay, so then the anti-differentiation step hasn't changed. 1/3 x cubed plus 4x. Boy, I'm getting tired of that. From -2 to 2. So let's see here. This would be -1/3 times 2 cubed plus 4 times 2. That's for the upper limit of integration, minus the lower limit. -1/3 times -2 cubed plus 4 times -2. And I do want to actually see how all this computes out, so let's actually crunch it. Let's see here. Actually, we did this before, but let's see. 2 cubed, that's -8/3 plus 8, which before was 16/3. Okay, minus, let's see, over here I'm going to have -2 cubed over 8, so I'm going to get -8/3 minus 8. That's going to give me -16/3, but what? It's minus a -16/3. What do I end up with? Okay. I want you to convince yourself that that answer makes complete sense. What were we doing? We were computing this area. How does this area compare to this area right here? It's twice the amount, right? By symmetry. Specifically, this function is symmetric about the y-axis. Okay. And since it was symmetric about the y-axis, we can make some sort of statement. So I want you to make this statement. Suppose f is even. Okay? Now, if you're not completely sure what an even function is, you might want to spend a little bit of time reviewing it. This is not a property that shows up all the time, but it is a helpful little time-saving property. Okay? Suppose f is an even function, then the integral from -a to a of f of x dx is just twice the integral from 0 to a of f of x dx. That's what we just discovered. Okay? Let's make sure this makes sense. There's two things I'm requiring here. What are the two things I'm requiring? I'm requiring f to be even, and what's the other one? Let's look at those limits of integration. They've got to be equal yet opposite. If that's the case, then rather than computing this definite integral, you can compute this one. Does that save you any time? To be honest, it doesn't save you that much time, but what's beneficial about this? What's beneficial about this? What do we get to plug into as a limit of integration? 0. We've already seen, oh, it's a lot easier to plug in zeros more often than other numbers. Okay? So that's where that's a little bit of a time saver. All right, next page. All right, we're going to keep going. Let's do a new function, though. I'm kind of over those quadratics. Let's do a cubic. Let's look at the function f of x equals x cubed, and I would like you all to compute this area right here. The area between the graph x cubed and the x-axis. You've got all the tools you need. Check with your neighbor. Make sure you're on the right track. You'll get an answer of 4. get done with that, go ahead and do number 8, which is the same thing with just a little bit more to the region. Okay. Come around. See how we're doing. Okay, so we ended up with the definite integral from x equals 0 to x equals 2 of x cubed dx, which gave us 1/4 x to the 4th evaluated from 0 to 2. Okay, do you need that evaluation bar?
Yes.
Yes. Okay, folks, what did I do from here to here? I took the antiderivative, so I'm done writing the antiderivative symbol. Right? All right, then this gives me 1/4 times 2 to the 4th minus 1/4 times 0 to the 4th. Could you just put a 0 there? Oh boy, you betcha, right? I'm just showing you the procedure. Okay, and we end up with 2 to the 4th is 16, divided by 4 is 4 minus 0, or 4. Okay. All right, what's going on here? Well, let's do the work. This is the antiderivative from minus 2 to 2 of x cubed dx, which is equal to 1/4 x to the 4th from negative 2 to 2, which is equal to 1/4 times 2 to the 4th minus 1/4 times negative 2 to the 4th. Which is 4 as before, but then what is this? Well, negative 2 to the 4th is 16, divided by 4 is 4. We get 4 minus 4, we get 0. Now this is not a horizontal line at the line, that's not the line y equals 0, when I'm asking what's the area underneath the curve in the x-axis. What's going on here? We found the net area. Let's be careful, net area as opposed to total. Okay, so we're not actually going to carpet this. Okay, we're looking for the quantity, and this came out to be 0. By the way, if we wanted the total area, what would the total area be? It'd be this 4 plus this 4, which is 8. Okay, but the net area here is 0. Okay, there is a little time-saving thing we can do here and say if f is odd, if f is odd, then what would be the integral from minus a to a of f of x dx? It would just be 0, because one way to look at that, and we're not going to make this statement, we're not going to prove this statement, but the antiderivative of an odd function is going to be an even function, and when you evaluate even functions at opposite domain values, you get out the same thing, so the difference will always end up being 0. Okay, if I said that too fast, just take this as a handy little theorem. Okay? So there are two things that we require. First, that the function be odd, but that's not enough. You also have to have equal yet opposite limits of integration for that to happen. Okay? So sometimes people only remember, oh, it's an odd function, the antiderivative is 0. No. Or the definite integral is 0. No. It's got to be opposite sides. For the one way to look at it is those rectangles are all perfectly canceling each other out. Okay, if you don't know what I'm talking about by the rectangles, watch the video. It was a nice one. Okay, get some popcorn, meet up with some friends. It's a lot of fun. Okay. All right, so you've got it. Okay, go ahead and work problems. I'll come around and help you. Okay, just keep on working until you get all the way through, until you can't get any further. So if you're watching the video at home, pause it so you can copy things down if you haven't figured them out. It's not for you guys here. All right, any questions on number A? Promise? All right. Number B. Doing okay? Watch it. I find now, okay, I messed up taking derivatives of the sine and cosine quite a bit early on because I have to keep that, now I have to keep it separated from antiderivatives, and that's a little bit, it's easy to make mistakes with those, right? So the antiderivative of the cosine is the sine. Why? Because the derivative of the sine is the cosine. But the antiderivative of the sine is minus cosine because the derivative of minus cosine is minus minus sine. Watch that. Easy to make those mistakes. Okay? I'll leave this up during the break so you can come copy down anything you're missing. Okay? I quickly answered this with 64, just like that. Not because I'm clever. What did I do here? I went back to what we're originally doing. What is this function here? Y, this is the horizontal line, y equals 8, right? So this is y and this is f of y. Okay, so first of all, the fact that I'm using y doesn't matter, right? I can use any variable I want and ask you to do this. Okay? What is this curve? Here it is. This is the curve y equals 8, right? And what are we doing? We're computing the area underneath the curve between -3 and 5. What is this shape, folks? It's a, actually, we need one better than a rectangle. It looks like a rectangle here, but actually it's a what? Even it's better. It's a square, right? What's the width? What's the height? 8. What's the area? 64. Hopefully you did it the long way and also got 64. Okay. Let's go ahead and make a comment on this. Let's go ahead and make a comment on this one. Okay? Just to see how where the fundamental theorem of calculus is coming in from. Okay, here was y equals 8. You don't have to write this down if you don't want to, because we'll go in more detail later. From 3 to 5. Okay. What did we do? Well, you guys who did the integral, which is what I wanted you to do, you found an antiderivative. The antiderivative of 8 was what? Well, it's actually 8 what? 8y. Make sure you've got y's there, not x's in your work. Okay. So here we have y, and this is the curve. This is the curve f of y equals 8y. Okay, that's the antiderivative, right? Now, what this is saying is that rather than computing area, which is a what type of problem? It's a two-dimensional, this is Calc 3 right here. Rather than computing area, which is a what type of problem? Two-dimensional problem. We go ahead and we plug into the function. We look at there's that function 0, and then when we plug in 8, we get 8 comma 64. And what do? We look at the difference between the two y values. What is the difference between these two y values? 64. So rather than computing the area, we look at the difference in the antiderivative values. There is something there. There's something to spend some time thinking on. Okay? All right. We'll do more of those in more fundamental theorem of calculus questions in 5.3. Okay. I don't have much to say about letter D. You got to know your derivative rules, or you can't do your antiderivative rules. All right? Okay. Any questions on D? Okay. Letters E and F were an exercise in the way sometimes authors will write things, which can be frustrating. Okay. What is the understood number being multiplied to dx there? 1. It can't be a 0, or there would be nothing there, right? The understood number is 1. Okay. So it's 1 dx, and what is the antiderivative of 1? It's x. We okay with that? Okay. Folks, I'm flying through this material, but I think you can hang on, but you got to let me know when I go too fast, okay? I'm purposely going fast through this material because I think you can do it, but if I make a mistake in judgment, you got to let me know, okay? All right. Letter F is, again, authors do this. You know why? Because if they write the problem this way, it saves them 1 millimeter of line space. Yeah. Okay. But every year I got to spend a lot of time explaining this problem, so their 1 millimeter of line space cost me a lot of time. They didn't ask my opinion. So I think it's easier to see the problem if you rewrite it. So rewrite this integrand this way. Okay. So it's customary if you've got a fraction for your integrand and the numerator is 1 to just put the dx there up in its place. I don't know why people do that, only I feel I probably ought to do it too, so that way you're exposed to it. Okay, not that I like writing it this way, I think it's silly. Okay, antiderivative of the natural log of x is, antiderivative of 1 over x is natural log of the absolute value of x. Do you need that absolute value? Yes. Technically, in this problem, you don't. But if the limits of integration were negative, oh yeah, you would definitely need it or you wouldn't be able to evaluate it. Okay? Of course, the natural log of 1 is 0, and since 2 is already positive, do I need an absolute value in my final answer? No, you don't. But you put it there, there's nothing wrong with that. How we doing, folks? All right, during the break, if you didn't get G, I'll let you take a look at it. G is simply an exercise in rewriting things with your power properties. Okay? For instance, the square root of x is x to the 1/2 power. Now this, to answer this question, I'm going to say, oh, this is going to be x to the 2/2 times x to the minus 1/2, which is x to the 1/2. Okay? Amy?
No, I see it, but it was tricky of you.
You see it, but you don't like it. That's all right. That's all right. You don't have to like math. It doesn't have any feeling. All right. This one, what did I do here? In my first step, I divided this, and different people did this different ways, and some of you, I liked your way better than mine. I divided this into both terms in the numerator. And I also rewrote it as x to the 3/2 and x instead of x cubed square rooted. Okay? And then between here and here, I said, well, that's x to the 10/2 divided by x to the 3/2. Subtracting gives me x to the 7/2, etc. Let me clean that up because that's just ugly to look at. Oh.
What is the other way to do it?
Well, it's just, so properties of exponents, you can use, there's many properties, so you can use it, you just do it many different ways. There's no, I don't think there's, if there was one way that was the easiest way of them all, I would do it. So it's not that I'm not showing you some other easy way, it's just, there's many ways you can apply exponential properties. Yeah. Okay. Folks, when did the well, let's see, this is maybe the best problem. Let me see up here. Let's actually go to this sine one. Okay. When were you done doing calculus? You were done doing calculus when you went from this line to this line, right? I think this is an important point to make today. You were done doing calculus when you went from this line to this line. What did you do from this line to this line to this line? You were just doing simplification steps, right? Okay? So please, I need you when you're working on these problems, you want to get the right answer. You get all the points if you get the right answer. But I need you to separate the calculus steps from just the tediousness of combining a whole bunch of fractional terms, which often happens in these problems. Okay? If you get stuck going from here to here, we need to have a chat. If you get stuck going from here to here, we need to have a chat. If you get stuck from here to here, just keep working on it and don't stress too much, because at that point you've gotten 4 out of 5 or 6 out of 7 or all but 1 point because you just can't simplify something, which you should learn how to do. But that's not what I'm grading you on. Okay. Jigbe.
Shouldn't cosine of pi be -1, and then there's a negative outside of the cosine, so that would equal +1. And then +1, and the answer should be 2.
Ah! Oh, good. It's a good thing I just said I could be lenient on these. Folks, what did I just, let me backtrack a little bit. Good catch. Good catch. Everyone hear the air? Okay. Going way too fast on these. So this should have been 0 minus a -1 minus a -1 minus 0. Okay. So that would have given us 1 plus 1, which is pushing a brain cells 2. Good catch. Questions on that, folks? Okay. Next page. So we talked about all these. Okay, great. All right, folks, if you can't evaluate the arctangent of 1, that's a conversation we need to have, but we'll do it another time. Simon.
Instead of -pi/4 for arctangent of -1,
Mm-hmm.
I guess we said domain. But
Yeah.
So 3 pi over 4 would be wrong?
Well, 3 pi over 4 would be wrong for many reasons. What is the arctangent of 3 pi over 4? Well, it asks the, what is the arctangent? So let's just say this. What is the tangent of 3 pi over 4? Oh, I guess it is -1, isn't it? Yeah, it is negative. It's just not in the domain. Sorry.
Okay.
Yeah. So it's not in the domain.
Oh, because it's an inverse.
Remember, we had those restricted domains here. And one way to look at it is, what does the graph of the arctangent look like? Hopefully at some point you saw it has asymptotes, pi over 2 and minus pi over 2.
So we're not going to be doing any like the plus n
Oh, no.
nonsense.
No. We don't do that. All right. All right, letter I. Okay. Letter I is a perfectly fair game test question. Give it a shot.
Want these like in decimals or in fractions?
Hmm?
Do you want one in decimals or in fractions, and how far do we round?
I think the answer is 54. We'll see. Okay, I don't want you to spend too much time on this. That's enough. All right, folks. This is a problem that you could work all the way through, right? It would take you some time to, this would be 282 over 20, x to the 20th power, right? Plus minus 299 over 12, x to the 12th power, right? And then you could evaluate all of those. Okay, could you get through this? Yeah, if you were on a desert island, you had all the time in the world, you could get through it, right? Okay. What do I recommend doing here? Well, this is not an even or an odd function, right? Too bad it's not. Well, what could I do? I could break up the problem this way. Did I restart the clock? Yeah. 282 x to the 19 minus 299 x to the 11 plus pi x to the 5th dx plus the definite integral from minus 3 to 3 of 3x squared dx. Okay. Did that help me? Well, first of all, is that a legal move? Yeah, because I am setting up to take the definite integral term-wise, which, how do we do definite integrals? By taking antiderivatives, and I can take antiderivatives term-wise. Okay, so that's certainly fair. Now, you may not know this fact, so here's a fact for you. If you've got, and this is only true for polynomials, if you've got a polynomial function and every term is raised to an odd power, that makes the polynomial an odd function. And if you've got a polynomial and every term in it is raised to an even power of x, then it's an even function. So I've just broken this up into an odd and even function. Okay? Why did I even think to do that? Well, I kind of got a suspicion when I saw that I had equal but opposite limits of integration. Okay? So this is equal to 0 plus 2 integral from 0 to 3 of 3x squared dx. What did I do, Jen? So I said all of this right here evaluates to be what? 0. How come? So we said if you have an odd function and you have equal and opposite limits of integration, then they just cancel the picture. So if you look at an odd function, an odd function might be doing something like this and then go down and then doing something like that. This region and this region always cancel one another out in an odd function because of the symmetry about the origin. So that's why that's 0. Okay? And then we said, for even functions, and this part's just being a little show-offski, okay? It's actually not saving me all that much time. Okay? But for even functions, you could go ahead and just double from 0 to that upper limit of integration. Okay? So this gives me 2 times, what's the antiderivative of 3x squared? x cubed evaluated from 0 to 3, which gives me 2 times 27 minus 0, which gives me 54. Now, to be honest, I probably wouldn't put that on a test, just because it works best if you see this nifty little trick, and I don't know if everyone would see that nifty little trick. Okay? But you could get through it the long way as well, right? You could certainly have taken the entire antiderivative of this expression and then evaluated the upper and lower endpoints. You would have gotten 54 as well. Questions on that, folks? All right. I want you to try letter J. Take a moment. So hopefully we see that for letter J, and actually this is one where you could FOIL this out to the 5th power and then do one more binomial, right? And then start integrating termwise. So you could do that. And maybe you'll think that's better than what we're about to do. I don't know. But let me show you the way we want you to do this problem. Okay? And in other ones, you have to do it this way. So we're going to use a technique called a U substitution. The U substitution is done to undo the chain rule. Okay? And think about that. I mean, the chain rule introduces new factors that weren't there before, making it complicated to go backwards. Okay? So the U substitution is a methodical way of undoing the chain rule. Okay? So it is the only integration technique we're going to teach in this class beyond the elementary ones that we've done. Is it a basic antiderivative, or could I use the power rule after I rearrange it? The only other technique we get in this class is that of a U substitution. Calc 2 picks up and starts teaching more integration techniques right off the bat. Trig substitutions, integration by parts, partial fraction decomposition, lots of other tricks that you can use. But the most common trick is still the U substitution. It's the most common one to use. Okay? How do you know if a problem is geared up for a U substitution? Well, what you're looking for in a U substitution problem is an expression and the derivative of that expression up to a constant. Okay? So I'm looking in this original problem here, and I'm looking for an expression and its derivative to show up. I think I see it. I think I see this expression right here, and its derivative shows up right here. You see it? Okay. By the way, this showed up perfectly, meaning the constants were just as I wanted them to be. So I'm going to call that a perfect substitution. Okay? In other problems, you might have to rearrange stuff with the constants to make the substitution work a little bit better. Okay? So this is what I'd call a perfect substitution. What am I looking for? I'm looking for an expression and the derivative of that expression. So here's what we do. We go ahead and we say let U equal the expression. We let U equal x cubed minus 3x squared. Okay? Now, in math, you can replace anything you want with any symbol you want. Okay? But the problem comes in how was that symbol, or how are those expressions tied to other expressions? So I cannot just put a U here and call it good, because how am I taking the antiderivative? With respect to what variable? With respect to x. So when I do my substitution, I also have to adjust the variable that I'm taking the derivative with respect to, and that's the tricky part of the substitution. And it will be for any of your, would be for other substitutions that you do in later on. Okay? So what I'm now going to do is I'm going to take du dx. I'm going to take the derivative of this expression that I just wrote. So I just wrote out this statement here, this function here. One way to look at it is I defined a new function u as an expression of x, and now I'm going to take the derivative of it. So what is du dx? 3x squared minus 6x, and it's the fact that this perfectly matches this that makes this a perfect substitution. Okay? Now, we're now going to do a little bit of manipulation symbolically, even though it's not really meaningful. I'm going to go ahead and multiply both sides by a differential x. I'm going to multiply both sides of this equation right here both sides by a differential x. Okay, let's do that. That gives me du is equal to 3x squared minus 6x differential x. Okay. Now, this is actually the substitution. So I was kind of hiding stuff from you a little bit, but I didn't want to talk about it until it was time. Here is the expression, and what is the derivative of the expression? This piece right here. What did I just do? I just also underlined the dx. Okay. So what am I going to replace u with? Or excuse me, what am I going to replace x cubed minus 3x squared with? U. What am I going to replace these two factors with? Du. Okay. So here we go. This is how the substitution works now. Okay. So in place of this piece right here, I'm going to write u to the 5th power. Okay. And then in place of both this factor and the dx, I'm going to substitute in a du. So we put just du here. Let me kind of clean that up. We write u to the 5th du. Okay? I don't expect you to get this my first pass. Usually people are very confused the first time I do this. So it's one of those situations where let me get through the first example, we'll do a couple more, and then we should start feeling a little more comfortable. Okay? So I adjusted not only the expression, now it's a u, but I also adjusted the variable of integration, which is the key part that makes this work. Okay? Put another way, the original problem had a lot of clutter in it, and I'm sort of avoiding the clutter with the letter u. It's now easier to look at this problem. I could have answered the question from here, but it's easier to look at this way. Okay? This is a change of variables to make our lives easier. Okay, let's take the antiderivative of u to the 5th. What is the antiderivative of u to the 5th? 1/6 u to the 6th.
Du.
Nope.
No.
We're just finding a general antiderivative here, right? As somebody pointed out, there are no limits of integration on this. I'm not asking for an area under a curve right now. I'm just teaching you this technique. We'll do it with areas underneath the curve later. Okay? All right, this part always sounds like I've got, well, I don't have good English anyway, but this part makes me sound even worse. Okay? Am I done with this problem? I was looking for an antiderivative of some function of x, right? I've given a function of u. But u wasn't the variable you were asked to solve for, was it? Well, what was u? Well, u was 3x squared minus 6x, right? So I'm going to take the expression and replace, the phrase we use is back substitute what u stood for.
I thought u was x to the 3rd minus 3.
Oh, my bad.
Okay.
Oh, golly. Oh, golly. Oh, I just screwed up the punchline of the joke. We got all the way through to the end and I screwed up the punchline. Okay. Folks, I have already said this. Which is easier, taking the derivative or the antiderivative? Taking the derivative. What should you always do after you take an antiderivative? Check your work, just to be sure. I especially encourage it for u substitution problems because in checking your work, you're going to get a better appreciation for how the u substitution works. Okay? So on another page, let's take the derivative of that, or somewhere else where we've got room. I'm going to take d dx of 1/6. What was in there? It was x to the 3rd, right?
X to the 3rd minus 3x squared, all to the 6th.
To the 6th plus c. Great. So I'm going to check my work by taking the derivative of this. Okay? By the chain rule, we've got an inside function and an outside function, right? The outside function is u to the, excuse me, well, it actually is u. The outside function is something to the 6th power, right? So that will be 1/6 times 6 times that something, all now to the 5th power. But by the chain rule, I now have to multiply by the derivative of what was inside there, which gives me 3x squared minus 6x, and of course the derivative constant is 0. So you see how we undid the chain rule with the u substitution. All right, I don't expect you to have mastered it this first time through. Okay, so we're going to do some more examples. Okay. Oof. Ugly, right? All right, let's do another one. Okay. Let me tell you my train of thinking, my train of thought as I go through this. Okay. The first thing I do is say, hey, was there a function that I learned when I took its derivative it gave me? X squared over x cubed plus 3? No, I can't remember one. Then I say, well, maybe I could break it up with powers, but what's the problem? The denominator has sums in it. I can't break that up. There is a technique you'll learn in Calc 2 called partial fraction decomposition to break that up, but that's a bear. Okay? So I don't want to do it. Okay? So instead, I start moving on to my other techniques of integration. Okay? And the most common technique, so the first thing I check is, well, maybe I should try a U substitution. So what's the hallmark of a U substitution? Well, I look for an expression and that expression's derivative up to a constant. If the constant isn't right, I can fix that. I see an expression here, and I'm just going to tell you the answer. I see an expression here, x cubed plus 3. I also see the derivative of that expression up to a constant. How come? Because what is du dx? It's 3x squared. I don't have a 3x squared, but I've got an x squared, so it's right up to a constant. Okay? Now, the next step is to multiply both sides by differential x, right? Okay. Folks, going forward, I will skip the middle step and I will go from here to here in one step, because that part always works out the same way. Okay? I'll let you decide whether you like showing that middle step or not. To be honest, I don't like showing that middle step, because then I forget to get the dx over here, which is what you have to do. Okay? All right. At this point in the U substitution, and some of you may have learned U substitutions before, so everyone kind of does them their own way. It's sort of like factoring. Okay? At this point in the U substitution, what I try to do is I try to make what's on the right-hand side perfectly match what I've got up there. What do I have on the right-hand side? I've got an x squared. Oh, there's an x squared. Times a dx. Oh, there's times a dx. But I don't have a 3 there, so I'm going to take this 3 over to the other side. So that's going to give me 1/3 du is equal to x squared dx. Okay. Now, I'm about to do the substitution. I would never do this on my own. I'm going to rewrite this as x squared dx all over x cubed plus 3. I would never do that on my own, but I just want to help you see how the substitution works. Because I need you to remember that this dx truly is a component. It's a multiplicative component of the definite integral. You saw that because that was the delta x from the video you watched. Okay? So it is just a multiplicative component, and so I can think of it as dx over 1 and then multiply the fractions together. Okay? I would never do this step normally, but I think it helps to see the substitution a little bit better. So what am I going to do? I'm going to replace the denominator, x cubed plus 3, I'm going to replace it with u. Then what am I going to do? I'm going to replace the x squared dx with what? 1/3 du. Okay. Now this is really 1/3 over u du, right? And what can I do with constants? Well, I can factor them out of antiderivatives. So I could write this as 1/3 integral of 1 over u du. Okay? I've tried to show you how you can move these around a little bit. You don't have to move them around the way I do, but this is all just related to, with multiplication, there's lots of ways you can write things. When you multiply fractions, there's lots of ways you can express stuff. Okay? This is probably the most natural way to do it. To be honest, if I were doing this on my own, I would go from here straight to here, just out of practice. Okay? And that's probably what my math lab will do, straight out of practice, but there's some middle steps for you. Okay? at long last, we kind of stopped thinking about the original question. We've created a new question with a new variable that is equivalent. Okay? And we go ahead and we take the antiderivative of it. What is the antiderivative of 1 over u? Natural log of the absolute value of u, and then I need to tack on a plus c here. Folks, one thing I didn't mention, I'm really lazy about that plus c. Technically, don't write this down. Technically, when I took the antiderivative, that got replaced with natural log of u plus c, and there's a 1/3 times that, right? But if I distribute 1/3 to each of those terms, what's 1/3 times an arbitrary number? Just another arbitrary number, so we just call it c. Okay? And you'll learn that math people are pretty lazy with those constants. Okay? So they don't they don't get all flustered with them. Okay? So anyway, it's kind of like negative signs in physicists. They don't care about negative signs. Each their own. Okay, so we end up with that. Am I done with the problem? It breaks my heart if you get to here and you don't answer the question because you're almost done. But what were we looking for? We were looking for an antiderivative of this original function that was given in terms of the variable x. So the phrase is we need to back substitute. What we say is u wasn't the variable you were asked to solve for, was it? No. Well, what was u? U was x cubed plus 3 plus c. On your own, please, please, please check that and confirm that you get the original the original integrand. Okay? We are undoing the chain rule, right? Having a lot of fun doing it. All right. I want to do a couple more. Folks, I am flying through these. Okay? You will get some practice. The hardest part of a u substitution is learning to spot it. Okay? Sometimes the best I can do is just show you, and now you've got a collection of examples. Okay? How am I going to do this one? Well, I think I'm going to rewrite this just so it's a little easier on the eyes. I'm going to rewrite it as the natural log of x times 1 over x dx. Oh, that's easier on the eyes. Do you see it? What am I looking for to use substitution? I'm looking for an expression and its derivative. Do I have it? All right, who wants to take a shot? Who's struggling with this? Who's struggling? Jen. Okay. What's the expression that shows up as well as its derivative? Ah. So I'm going to let, because I have a choice here, right? I could let u equal 1 over x, but what's the derivative of 1 over x? It's minus 1 over x squared. That doesn't get me anywhere. So I'm going to let u equal the natural log of x. Okay? I'm going to just do this step now. What is du? It's 1 over x dx. Really what I started was I had du over dx equals 1 over x, and then I multiplied the dx over. But nobody ever writes that step. They just go from here to here. Okay? I think I'm all set, ready to do the substitution. This is an example of what I called a perfect substitution again. Thank goodness. They're a little bit easier. Okay? So this is the integral of u du. What did I do? In place of the natural log, I put u. And in place of the 1 over x dx, I put du. Here we go. We sort of forget about the original problem for a moment, and we just take this new antiderivative. The antiderivative of u is not 1, that's the derivative. Go the other way with the power rule. Since the power here is 1, so it's add 1 to the exponent, so now it's u to the second, but divide by that new exponent. Plus c. Okay. Okay. Okay, because we're back to asking for a family of functions, all of whom have the derivative that is the integrand. We're not looking for the number that is the area underneath the curve, although we'll get back to that in the next problem. Okay, but u wasn't the variable as you was asked to solve for. What was u? U was again, please on your own time, take the derivative of that and confirm that you get the original integrand. Okay? That's how we're undoing the chain rule. All right. All right. This problem is harder. One, it's not going to be a perfect substitution. We'll see that. This problem is harder because now I'm looking for what? The net area underneath this curve. Right? And I could go into Desmos, I could graph that function, and then try to find the area underneath the curve between 0 and pi over 2. Okay? Completely fair game question. Okay? But it would sure be easier if I didn't have so much clutter to look at. So I'm going to do a U substitution. But what else is different? Why is this not like the U substitution before? You said it was somebody said it was a net area, and what physically shows up in a net area problem? What's that? What do you mean? Well, the answer would be a number. I agree. I've got limits. I'm not sure. Maybe you guys are saying I've got limits of integration to this. So I've got to also work with the limits of integration. So I do this a little bit differently. Because as Amy said, I'm looking for a number. I don't care how I arrive at that number. I'm not looking for a particular function. Okay? So when I do my U substitution, everyone listen to this, make sure it makes sense. When I do the U substitution, I'm not going to back substitute. When I do the U substitution, I'm going to also adjust my limits of integration so I can keep moving in the forwards direction. Okay? Let me show you what I mean by that. Okay? First of all, we got to do the U substitution. So let's see here. I'm going to let U equal, again, this is something that I've done a million of these, so it's completely obvious what I should let U be. It might take you a little bit of trying. Okay? If I, don't write this down, if I let U equal 2 cosine of x, the du would be minus 2 sine x. I've sort of got that up to a constant, but what's the problem? Well, this dx, what's the problem? Well, this would go up in the dx would end up in the power, and that makes no sense, right? And it doesn't really actually substitute because I no longer have this times this. You guys couldn't see that. This times that. Okay? So that's not going to work, but it's worth a guess. And what I would encourage you to do is if you're dead stuck on a U substitution, make a guess and try it out. There's only so many factors in there anyway, right? So make a guess, try it out. If it doesn't work, you chose poorly. Try something else, right? All right. So instead, I'm going to let U equal 5 sine of x, and I want this constant. I've learned that when I've got just constants added or subtracted, I go ahead and rope them in as well. Just like we did on the last one. We didn't let U be x cubed. We let U be x cubed plus 3, I think it was. Okay. So then, what is du? du is equal to 5 cosine x dx. No, just take the derivative of this. What's the derivative of 5 sine x? It's 5 cosine x. But you've noticed something, Amy. This is not a perfect substitution. Okay? So the way I like to do this is I start looking ahead. How am I going to, well, in place of the dx, okay, there's a dx there. There's a cosine, but what else do I have? I've got a pesky 5 in my substitution. So what should I do with it? Take it on over to the other side. Okay? So we get 1/5 du is equal to the cosine of x dx. So I'm going to start the substitution even though I'm not actually truly ready for it. Let me write it down here. I'm going to start the substitution even though I'm not truly ready for it. Okay? So I'll have the integral of e to the u, right? Okay. And then in place of cosine dx, okay, and again, where else I could move, if you wanted to take a line, you could move this cosine factor so it's touching the dx factor so it makes the physical substitution that you do seem easier to see. Does that make sense? But you don't have to, and I never do. Okay? So in place of this factor and this factor, in place of the product of those two factors, I'm going to put a 1/5 du. So that's going to give me, well, we had that 2 that was already there. And then here's the 1/5 du that's replacing cosine x dx. It's 1/5 du. To be honest, what I would have done in reality, in one step, I would have just brought that 2/5 outside e to the u du, like that.
We're not done here.
No, we're not even close to being done here. What did we say would made this problem hard? It wasn't the u substitution, even though this wasn't a perfect substitution. What was hard about this was the limits of integration. Okay? You might have stopped writing it. I've stopped writing it, but this actually says x equals 0 to x equals pi over 2, right? And I said when you do a substitution, you must adjust everything. So now I need these to be u equals something to u equals something. Remember those limits with the u's? You also had to adjust your limiting variable. It's kind of the same idea. Okay? All right. This part's always a little bit confusing the first couple times through. Besides being my substitution right here, you can think of that as a formula that relates u and x together. So when x equals 0, what is u? Well, u would be 5 times the sine of 0 minus 4, which is, what's the sine of 0? It's 0 times 5, so you get minus 4. So what's my lower limit of integration? Minus 4. That's tough, folks. Okay? So besides being, so let me just reiterate that. For this expression right here, besides being my substitution, it's also a formula. It converts my x values to u values. Okay? That was for the lower limit of integration. Who'd I lose on that? I ain't scared. Don't be scared. I'll call on you, but that's okay. Haley, I lost you on that. Great. Let's see what we can do. So we just adjusted this for the lower limit of integration. What's our upper limit of integration originally?
5 sine of x squared.
Oh, no, limit of integration up here.
Oh, just kidding.
Huh?
X equals 0 and x equals pi over 2.
So the upper one is x equals
Pi over 2.
pi over 2. So when x equals pi over 2, I'm going to take this expression right here and say that u is what? I'm going to take this expression, I'm going to substitute in for x, I'm going to substitute in pi over 2. So what is u? U would be 5 times the sine pi over 2. How are we doing?
Okay.
Minus 4. Okay? Folks, this is really one of those things. Once I can just have a dialogue one-on-one with you, I can get it clarified just like that, I feel like. Do we feel better about that?
Yeah.
Okay? So please let me know what your questions are. All right. So let's see. Sine of pi over 2 is 1 times 5 minus 4. We get that u is equal to 1. So my upper limit of integration here is 1. Okay? Let me give myself a little bit of room because, boy, that's gotten a little cluttered. So this is the integral from minus 4 to 1 of 2, oops, what did I do? I had 2/5 here. Yeah, 2/5 e to the u du. Okay? So notice, because I've maintained I adjusted the limits of integration, there's no reason to back substitute. I'm just going to find the number that is this answer, and it will be equivalent to the number from the original problem. Okay? So, help me out, folks. Antiderivative of e to the u? It's e to the u. So we get 2/5 times e to the u evaluated from minus 4 to 1, which is 2/5 times e to the first minus e to the minus 4th, and I think that's all I can do. Park it there.
For every problem like this, we're always
Uh-huh.
going to use the what you set u to be.
Exactly. We use that as a formula to also adjust our limits of integration. Yeah, great point.
So because of this problem being an upper and a lower limit, we don't need to
Yes.
Because,
Yes.
okay.
Yeah, so the, at some point maybe I'll clarify that. Remind me another time to clarify that. I want to keep moving. But yeah, the fundamental theorem of calculus said for any antiderivative, so I am always picking the antiderivative where the c value is 0. But if I picked any other number, I would have plus 20 here, but that would give me a e to the first plus 20 minus e to the minus fourth plus 20, but the 20s would always what? Cancel out, so it doesn't matter the choice. Yeah. Great questions. Yeah, so let's just reiterate what this original problem was. We've got some funky curve here. I've got no idea what this curve looks like. You should plot it in Desmos just for fun because you're curious mathematicians. Okay? Got no idea what this curve looks like. I've never even thought to graph this curve. Okay? We're trying to find the area underneath it between 0 and pi over 2. We found that the area is this nasty number. Oh, don't be rude. It's this number right here. Right? It's a mess, but what is it? It's a number. Just like any other number. Okay? All right. All right, let's do this again. Okay, I'm going to erase this because I'm out of room. Okay, last one. Before we move on to more topics, don't get excited. Okay. Last one. Okay. So this is going to be a U substitution where I also have to adjust the limits of integration. We're going to learn a nifty little trick here too. Okay, so this is worth showing you. Okay, so I'm running through my rules of how to take antiderivatives, right? And I say, well, is this an elementary antiderivative? And if you said, ooh, maybe, I'd agree. We're kind of close. This sort of looks like the antiderivative of the arc secant. This sort of looks like the arc secant, right? Sorry, not arc secant, arc sine. Because we've got something squared minus x squared inside a square root in a denominator. Okay, so watch that. Remember, just little adjustments to the integrand makes the problem significantly easier or significantly harder. And so it's kind of hard to just first value say that's a hard problem, that's an easy problem. Okay? What I'm saying is if it were this, I could probably get there just by doing some interesting factoring. Maybe not, maybe not. Okay? But certainly if it was this, I could get there with some interesting factoring and just go ahead and use the antiderivative, or just use the derivative of the arc sine to get there. Okay? But that's not the case. How come? We got a pesky x factor there. Okay?
But we can like rewrite it.
What's that?
Rewrite it.
We could try to rewrite it, bring it down as x to the minus 1. Can't do it. I mean, you could do it, but it wouldn't help you.
Can you substitute it?
So yeah, so we're stuck. It's not an elementary rule. Power rule is not really going to help me because of this. I've got two terms inside that square root. If it was just an x squared inside the square root, sure, use power properties. Because we got a sum inside that square root, it's not going to work. So what are we left with? Well, your toolbox right now is pretty sparse, right? So what tool are we going to use? U substitution. What's the hallmark of a U substitution? We're looking for an expression and its derivative up to a constant. Okay? So let's let U equal 25 minus x squared. That's pretty ugly. Let's let U equal 25 minus x squared. That makes du equal to minus 2x dx. It's not a perfect substitution. Do you see it? We're off by a little bit. So let's divide that negative 2 over. So we get negative 1/2 du is equal to x dx. By the way, everyone teaches U substitutions their own way. Okay. So other people you show this to might say, oh, that's not how I do it. Fair. Okay. All right. Now, we also have to do what in this problem? Adjust the limits of integration. Okay, who had trouble last time with adjusting the limits of integration? I don't believe you. Kasha. Great. All right, so what's our lower limit of integration currently? It's currently what?
0.
X equals 0 specifically, right? It's currently x equals 0. Okay, so now I'm going to use my substitution formula as a way to get the new limits of integration. Okay. So I'm going to write when x equals 0, what would u be? So I take 25 and I substitute in a 0 for the x, and I get 25. Okay? Who else? Sometimes it's just that yes-no questioning, I think that clarifies things. All right, well, you write the second part for the upper limit of integration. That's all the time we got. When x equals 3, u is equal to, you all got it, 16. Great. Everyone okay?
So are the numbers going to be flipped?
Let's talk about that. We'll get there here. Yeah, we'll get there. So let's go ahead and just rewrite it. So we get the integral from u equals 25 to u equals 16 minus 1/2 1 over the square root of u du. Everyone see what I did there? Why is the minus 1/2 out in front? Because that's where I like my constants. What's that? Why is what flipped? So they're not flipped, right? What was the original lower limit of integration? It was 0, and when x is 0, we find u is 25. So for the new lower limit of integration, I did put 25, but you're on to something. You're on to something, okay? You could do calculus this way. It all is internally consistent. It works out just fine, and you would still get the correct answer. But usually, as Jen said, as Simon said, we want our lower limit of integration to be smaller than the upper limit of integration. Okay? Well, never fear. We've got a handy formula. Okay? That's related to if you change the sign on all the delta x's in that Riemann sum, it basically tells us this, that if you have the integral from a to b of f of x dx, you could rewrite this as the integral from b to a. If you want, you could interchange the limits of integration, but you would have to change the sign on the output. Because now all your delta x's go in the opposite. You start at the right-hand side moving left, so all of your delta x's will have a negative value for them. All those negatives could factor out, and we get this. Okay? So here is a handy fact. Okay? So let's put that into play. So I could do calculus this way, no problem, but it's kind of like, it's kind of like everyone likes to have the leading coefficient of a quadratic be positive, right? We kind of like that to happen, so we do some adjusting so we can factor that way, right? So kind of the same idea. So I'm going to go ahead and interchange the limits of integration, but how do I pay for it? I have to change the sign on the integral, which in this case would make it a positive 1/2. But don't think of it as negative or positive. Think about changing the sign. Okay? So this gives us 1 over the square root of u du. At long last, we're ready to tackle this definite integral. How should I rewrite this, though? Unless you're good at this. Well, maybe you're fine with it. I'm going to rewrite this as 1/2 integral from 16 to 25 of u to the minus 1/2. I'm not going to lie, I have a hard time integrating some of those square roots. So I go back to my power functions. Differentiating, I'm pretty comfortable. Integrating, not so much. In a year, you guys will all be better than me at this, so you'll be fine. All right, here we go. We get 1/2. Add 1 to the exponent. It's now u to the 1/2. Divide by the new exponent. Dividing by 1/2 is the same thing as multiplying by 2. Evaluate it from 16 to 25. So that gives us the square root of u evaluated from 16 to 25, which is the square root of 25 minus the square root of 16, which is, fingers and toes, 1. Yeah, don't judge an ugly problem by its cover, right? This came out really nice. All right, we're having fun. All right, I got to do a couple more things. And we're not going to get through every example on here, but I got to do a couple more things. Obviously, we're not going to get through all these things. But I think we can do a couple more things that will finish us out so you guys can start doing a lot of the work. Okay? The first thing is how do we find the average value of a function? Okay? I'll explain this in more detail later. But this expression here gives me a what? What does this expression give me? A net area. It gives me the area underneath the curve. If I want to know what the average height of a function is, I take the area underneath the curve and divide by the length. Oops, I don't know why I wrote that. Sorry, that's nonsense. I'm getting tired. I should have written b minus a, the length. Sorry, that was nonsense.
Didn't help us conceptually see though.
Okay. All right, so first of all, why would you want to compute the average value of a function? Let's say your function tells you the temperature at any point in time during the day. Well, then a natural question you might want to ask is, okay, what was the average temperature for the day? Okay? So there are lots of instances where you might want an average value. Okay? So again, if I took something like this function here, sometimes it's up, sometimes it's down. What's its average value? Well, maybe you would guess that its average value is something like this. What are you really doing? You are constructing a rectangle that has the same area as the area underneath the curve. And then if you want to know the height of that rectangle, what do? You take the area of the rectangle and you divide it by its length, and that'll give you its height. Okay? So we find the area underneath the curve, and then divide by its length, and you get the average height. It's a clever little trick. Yeah. We're having fun. Okay? This one's not an exciting answer, but I want to do it so you have a problem in your notes. Okay? Here's the sine curve between 0 and 2 pi. What's the average height of this function between 0 and 2 pi? 0. It's not a very exciting answer, but we'll at least do the work. Okay? So we would say that the average value of the function is 1 over 2 pi minus 0 times the area, which would be 0 to 2 pi of sine of x dx, which gives us 1 over 2 pi times the cosine of x, let's see, times the cosine of x evaluated from 0 to 2 pi, but that gives us 1 over 2 pi times cosine of 2 pi is 1 minus the cosine of 0, which is also 1, which is why we end up with 0. Not a very interesting result, but at least you've got an example of this expression. Oh, yeah. Sorry. Minus, minus, plus. Yep, good catch. Good catch. Yeah, the antiderivative, folks, I'm sorry, I'm going a little faster. The antiderivative of the sine is the minus cosine. Good catch. Everyone all right with that? All right. So for a much more interesting one, you should try this. Okay? This, and look at the graph, too. It's a much more interesting problem. Okay. We'll get to this story problem next time. All right. So in the time I have remaining, I want to do two things. First of all, we can now answer the total area questions. They're not really any harder. It's just you have to remember that the definite integral computes the what? The net area, and then you have to make adjustments accordingly. Okay? So the total area is the integral from 0 to 3 of the absolute value of our function. Okay. Let's just look at graphically what's going on here. If I were to factor this function, I believe it factors to be 4x times x minus 2 times x minus 4. Yes. Okay. That's how it factors. Okay. So the graph of this function looks something like this. Okay. Where here is 0, here is 2, here is 4. Okay. I don't have those turning points just right, but I'm not worried about that. Okay. And I'm asking you to find the area. I'm asking you to find this total area. Okay. Now, I'm not asking for net area, right? This is literally if I wanted to carpet this weird shape in my room, how much carpet would I need? Okay. So I want this to be counted as both, I want both of those to be counted as positive when I want total area. Okay. So this will do that. How come? Because the absolute value takes the part below the curve and flips it up, right? And so then the definite integral would count it all as positive, right? Well, how do I take definite integrals with absolute values? I don't know. You could do it. It's a little bit of work. But the easier way to do this is to simply break it up into subregions and then adjust the signs of the subregions if needed. That's all you do. Break it up into subregions and then adjust the signs of the subregions if needed. Okay, let me, that's a little bit big. Let me make it a little bit smaller. 0 to 3 absolute value of f of x dx. So what am I going to do? Well, let's first take this region right here from 0 to 2. Okay. Plus the integral, well, let's be a little careful there. Let me put the sign in. Then we'll take the area of the second region. So let's go from 2 to 3 of f of x dx. But what will be the sign on that subregion? When we do the definite integral, which does compute net area, it will compute it how? As negative. But I want it to read it as positive. Change the sign. No, because because we're looking for total area, and I'm doing what this absolute value function would do. Mm-hmm. Yeah, Alejandro.
So you don't need to write the absolute value?
No, because basically we just did the absolute value. Here, let me show you. Maybe here's another way. This might make a little more sense. So let's just put plus as we always would in breaking up two regions. So we'll go from 2 to 3. But then what is... how do I take the absolute value of a function when it's negative? I change the sign on it. So it would be inside here, I'll write minus f of x dx. But what could I do with that negative sign? Factor it out. So maybe that makes more sense. Yeah. In fact, I think I'll do it from that way from now on. Okay. I'm not going to compute these. Does everyone feel like they can compute each of them? Okay. A little bit messy, but actually not the worst thing in the world because I've got a 4 here. When I add one of the exponent divide, at least don't have fractions. Okay? I can't remember what the answer is. I'll let you check. Okay? All right. Last thing. So all of this has been finding the area. So when we find the definite integral, we've been finding the area between the curve f of x and the what? And the x-axis, right? That's what we've been finding. But suppose we have this question here, where we've got two curves. We've got f of x, and we've got the curve g of x. This don't have to look the same. We've got the curve g of x. Okay? If we want to find this net area between a and b, okay? The way we could do it is we could first, so let me just show you the logical answer, and then we'll shortcut that. The logical answer says first compute this area right here, which is the area between f of x and the x-axis, and then what? Then compute this area right here, and then subtract the red area from the blue area, and we'll have the area between the two curves. Okay? But the net result of that is really just saying to find the area between two curves, between a and b, we're going to take just the difference between the two functions. In fact, let me just write it this way. It will just be the upper minus the lower. That's the only thing you have to be careful of, is you taking the upper function minus the lower function. Okay? That works whether you're in the first quadrant, like I drew my picture, or anywhere else. By upper, I mean the one above, one with the greater than values. That will always work. Okay?
You're still evaluating both.
Yes, but what this did is, so what you would have done is, so we would have done, this is the upper curve, right? And then we're subtracting from it the lower curve. But I could put those together as a single integral if I wanted to, and what would it look like? It would look like the integral from a to b of the upper, which is f of x by my picture, minus the lower, which is g of x by my picture, putting them together in a single integral. So this is upper minus lower. Did I answer your question? No.
No. When you're looking at what points are you evaluating in upper and lower, A and B for both, or?
No, by upper, lower, I mean which curve is above the other one.
Okay.
So f of x is above g of x here. So I would put f of x first and then subtract from it g of x.
Okay.
Now that's important because if it switches midway through the problem, which one's on top, then you have to break up the integral there and change which one you list first. Does that make sense? So we will look at examples of that next time, but we're at least getting all the material out of the way. So let me just show you this picture here. Let me just show you this picture, and then we'll walk away from it. But let me put this up here. Okay, the graph of 6x looks something like this. Okay. The graph of this quadratic looks something like this. Oh, sorry, we gave it a name. It's y equals 3x squared minus 8x. Okay? So, what am I going to do? Well, I want to find this area right here between the shaded regions. Okay? So I've actually got a couple of tasks, and I'm going to skip over one of them. One task is to simply find out what will my limits of integration be. Well, I think we can see that I'm going to start finding the area where? At x equals 0. Okay? So I'm going to start finding the area right here at x equals 0. But the question is when am I going to stop? And the answer is at that x value. So what do I have to do? Maybe a system, or at least by substitution, figure out where these two equations intersect. Right? And that would simply happen when 6x equals 3x squared minus 8x. And I computed that before class, and I got 14 thirds, comma, 28. Okay? So we're going to set up but not solve this problem. The area between the two curves will be the integral from 0 to 14 thirds. Will be the integral from 0 to 14 thirds of which curve is above? 6x. Okay? We see that 6x is above the other curve. How come? Well, from our picture. What if you didn't have a picture? Then plug in a test point. Plug, for instance, 14 thirds. You can plug 1 into both functions, and which one's above? Okay? And you'd find that 6x is above. Okay? Minus the lower curve. Who's the lower curve? 3x squared minus 8x. And we're set. We can find the area now between two curves. It's an extremely adaptable, this definite integral is extremely adaptable. Okay?
The blue curve like dips underneath the x-axis.
That's okay. That's okay. Because I'm subtracting a minus. Yeah. So it all works out. This is the beauty of this. It's wonderful. All right.